So first of all, does anyone have any questions about the vector review or the problems? I'd be happy to go over any of those. Okay. Um, we're just going to keep sort of going with the mathematical preliminaries. I think the only thing we have left to do with that is matrix multiplication. And then we'll start getting into really the key definitions of this class, stress and strain. Um, so, okay, matrix multiplication. Um, So matrix multiplication depends on the idea of the dot product. So remember, so it depends on the dot product. Let's just remember what that is. Um, so if you have two vectors, let's say 2, 1, -2, and you're dotting it with a vector -5, 0, 6. The dot product would be multiply the two x components together, add that to the two y components multiplied together, add that to the two z components multiplied together, and I think in this case you get -22. So notice that the dot product is always, it gives a single number, a scalar value. That's why sometimes people call the dot product the scalar product. The output is a scalar, unlike the cross product where the output is a vector. As far as matrix math goes, you can write this two different ways. You can write it as a dot product like this, or you can write it where the left vector is a row matrix and the right is a column matrix, and you're just simply multiplying those together. So without the dot notation, this means the same thing as 2, 1, -2 like this, -5, 0, 6. Okay, and I'm telling you that other notation for it because it's going to make sense why matrix multiplication works the way it does. So matrix multiplication is just a series of dot products between rows of the left matrix bless you, and columns of the right matrix. Okay, so if we're multiplying the matrices 1, 2, 3, 4 to the matrix 5, 6, 7, 8. The way this works is, well, let me write this below and then I'll go up and do the calculation. So the ij element of the product matrix is the dot product of the ith row of the left matrix and the jth column of the right matrix. Okay, so did you highlight the what? Yeah, so I'll go through that right now. So this is kind of like the rule, but it'll make more sense when you just see it done, I think. So, okay, what this says is, so let's go through the elements of the product matrix just one by one. So first we want the 1, 1 element, okay, like the top left element of this product matrix. So to get that, we're going to take the dot product of the first row of the left matrix and the first column of the right matrix. Okay? So that is going to be 1 times 5 plus 2 times 7. Okay? And that's the 1, 1 element. And now we'll do the 1, 2 element of the product matrix. Okay? So that is going to be the dot product of the first row of the left matrix with the second column of the right matrix. Okay? So that is going to be 1 times 6. Right, 1 times 6. Right, plus 2 times 8. And now we want the 2, 1 element. So we want the second row of the left matrix dotted with the first column of the right matrix. So that's going to be 3 times 5 plus 4 times 7. Okay. Oh, I forgot to erase these. And then the last one, we want the 2, 2 element of the product matrix. So that's going to be the second row of the first matrix dotted with the second column of the right matrix. So that's going to be 3 times 6 plus 4 times 8. And if you do all this addition and stuff, in this case, you get 19, 22, 43, 50. And on TI calculators, and probably any graphing calculator, you can do matrix multiplication. Matrix multiplication is a super pain to do by hand, but calculators do it instantly with just using the multiplication symbol, the regular multiplication symbol. You have an 84, you have to like program an 85. It's basically the same thing. You do, it's a little tedious, a lot of clicks and stuff, but yeah, once you get the matrices entered into the calculator, then you're just using the multiplication symbol. So, you know, thinking through like that, I mean, I can check it right now on my calculator. So 1, 2, 3, 4. So now I've entered the first matrix, and I'm going to multiply that by the matrix 5, 6, 7, 8, and 19, 22, 43, 50. So you don't want to be doing this stuff by hand. You want to get comfortable with doing it on your calculator. Um, there are a few sort of mathematical things I want you to know about matrix multiplication. Um, and the first one is for a matrix product to exist. So what I'm saying here is you can't just multiply any two matrices. There are rules for what matrices can be multiplied together. For a matrix product to exist, well, think about what it takes for a dot product to exist. Uh, the length of the two vectors have to be the same. And so what this means is for a matrix product to exist, the left, let me say, the number of columns on the left and the number of rows on the right must match. Okay, so let's look at the example we just did. The number of columns on the left matrix is 2. The number of rows on the right matrix is 2. And so that's why we were able to do that calculation. Those numbers match. The second thing to keep in mind is if the left matrix has size m by I, and the right matrix has the size I by n, and notice that the number of columns on the left and the number of rows on the right have to match. That's why those i's are the same number. Whatever I is, it could be 50 or 2 or whatever. But then the product matrix, who wants to guess what the size of the product matrix would be? Yeah, perfect. The product matrix has size m by n. And you saw that with this, simple case. These are 2 by 2s. So we had a 2 by 2 on the left, a 2 by 2 on the right. The i's that matched for both of them were 2, and then our product matrix was 2 by 2. Okay, sort of a boring case, but you can see that it agrees with that. The third thing to remember is that order matters in matrix multiplication. So AB is not in general equal to BA. And in fact, there are cases where, say, A times B exists, but B times A doesn't exist. Okay. And then the last thing worth keeping in mind is that the grouping doesn't matter. If you're doing if you're multiplying more than two matrices. So, okay, grouping doesn't matter. And so I'll write that as what we can just call A times B times C. You could calculate that as A times B, and then multiply the product of that times C. Or you could first multiply B times C, and then put, multiply A to the left. But you can't change the order of that those are in, or the answers will be different, or maybe not even exist. Any questions about that? Okay, so let's just do one quick example. So let's say we have a matrix 1, 2, 3, 4, 5, 6, and another matrix 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we want to know two things. First, does this product exist? And then second, what's the size of the product matrix? And then how about this? Does the product matrix exist if you switch the order? Okay, so first, does this product exist?
It does, right? Because the left one is 2 by 3 and the second is 3 by.
Yeah, I mean, to me, the way to think about it is just think about one of these dot products, So we're always going to take a dot product of a row on the left with a column on the right, and the question is just, do those have the same size? In this case, those both have a length of 3, so that dot product exists, and that means that the matrix product exists. So the left is, let's say, 3 columns on the left, 3 rows on the right. So it does exist. Next, what's the size of the product matrix? So this left one is 2 by 3. The right one is 3 by 4. So what's the size of the product matrix?
Will be 2 by 4.
Yes, exactly, 2 by 4. That's how you make 2 by 4s at Home Depot. And then the last question is, if you switch the order, does this product exist? Well, then you'd be trying to, so if you imagine flipping these around, you'd be trying to take a dot product of this with this. Those don't have the same length. And so, no, that does not exist. Okay. Anybody have any questions for now about matrix multiplication? So this is helpful stuff to know. I'd recommend that you try to remember this notice type stuff, but really when you do it in this class, you're always just going to be plugging it into a calculator. Okay. So really what you should be doing when I give you the matrix assignment stuff is get familiar with entering it into your calculator and doing it in your calculator. Okay. Um, okay, so now we're going to get into sort of the definitions, the main definitions in this class. And this, I guess maybe the rest of the lecture today is going to be a little sort of philosophical, and then we'll move back towards um, kind of nuts and bolts calculations. So, okay, the first thing we have to talk about is the stress tensor. Like, really, this class is about definitions of stress and strain and understanding stress and strain. So, the first thing we're going to understand is stress. So, the stress tensor. And the stress tensor is a measure of the loading of a material at a single point. And that's why you can imagine that that's a very helpful thing to know if you're trying to figure out if a material is going to break at a certain point. You'd like to know how much it's loaded. And so that's what this is going to get at. Before I start talking about the stress tensor specifically, let's talk about what a tensor is. So first, what's a tensor? Well, it's analogous to a vector. So let's think about what a vector is. Okay, so let me write something that you might sort of think of as a vector. 5, 4, -2. Okay, we're used to thinking of that as a vector, but really that's just a list of numbers. You know, in a matrix, in a 3x1 matrix form. What would make that list of numbers a vector is associating each element with an axis of a coordinate system. So associating each element with a coordinate system axis. Okay, so if we interpret this to mean 5 times I plus 4 times J minus 2 times K, that's a vector. Okay. So it's the association of the list with a coordinate system, or the association of the matrix with the coordinate system that makes it a vector. Tensors are the same way. So 2, -4, 6, 0 is a matrix. But associating those matrix elements in a certain way with coordinate axes is what makes it a tensor. So I'm not going to tell you, like, we're not going to go into detail what this stuff means, but so 2 I tensor product I minus 4 I tensor product J plus 6 J tensor product I plus 0 is a tensor. So it's important to know that with vectors and tensors both, uh, those things are those things have relationships to coordinate systems. Okay. So again, it's the relationship between the matrix and the coordinate system that makes it a tensor. And yes?
Following the matrix, if the bottom right corner had a variable in a constant, would it be just the J symbol?
Yeah.
J hat.
J tensor product J, it would be in the
J tensor product.
Yeah. But so this idea is going to be important. Because these stress tensors are tensors, we're going to be able to convert from one coordinate system to another using a specific kind of math that if it was just a matrix, we wouldn't be able to do. And now let's start thinking about what stress is. So that's called tensor product, but that's never going to come up again in this class. But that's what it's called. And if you ever took a class in tensor math, like later on, you would talk about that thing. Okay, so now we're going to talk about the stress tensor. And the stress tensor is a connection between two things, a matrix and a sort of physical diagram. So the matrix will look like this. So it's going to be a 3x3 matrix, and I'll write it as sigma xx, sigma xy, sigma xz. Then I'll repeat sigma xy, then sigma yy, then sigma yz. Then I'll repeat sigma xz, sigma yz, and then finally we have sigma zz. And notice there's 9 elements in there, but only 6 of them are independent. We repeated 3 of them. And so we can write it as just a list of 6 elements. And I'll do it in the order sigma XX, sigma YY, sigma ZZ, and then sort of an order that seems odd, um, sigma YZ, sigma XZ, sigma XY. And now the physical diagram is this. So we have a cube. And we're always going to assume when we draw this cube that our coordinate system is like this. The x direction is this way, y is this way, and z is this way. And the relationship between the diagram and either one of these two matrix representations is this. The sigma xx means this. The sigma xy means this. And it also means this. The sigma xz means this. Sigma yy means this. Sigma yz means this. And it also means this. And I missed one connection here. This one is also sigma xz. And then zz is coming straight out of that z face. Okay, so we're going to want to be able to go back and forth between these two mathematical representations and this physical representation. But now I'm going to go through kind of explaining what these things all mean and why it helps us know anything about the loading in a material. So the question is, how do these 6 values give us the loading at a material point? Okay. So let's think about, so let's say you have just some arbitrary material and you want to calculate the loading at some point. And I'm going to represent that point by a infinitesimal cube inside there. Okay, so what's the loading felt by this cube? Well, think back to statics. A cube has 6 faces. And each one of those faces makes a fixed joint with the surrounding material. Okay, so 6 faces, and each face makes a fixed or a weld joint, with the surrounding material. So what kind of loads are applied to an object by a fixed joint. You know, think back to, this is all three-dimensional now. So what are the three-dimensional loads that are applied to a body by a fixed joint?
Stress, shear, tension, shear, and rotation.
That really is in 2D. That you're definitely on the right track. But remember, so now we're talking about 3D. So think about degrees of freedom. Like, think about this thing. It can translate in any one of these three axes. So that's three forces that need to be applied to hold it in place. And it can rotate about any of the three axes. I don't remember which one I did. And so you need three couples in order to keep it from rotating, right? So each one of these faces, stupid computer. So each face is acted on by a full vector of forces and a full vector of couples.
When you say full vector, is there going to be situations where you have like partial vectors of cup, or is it not?
Well, I guess all I'm saying is none of those are automatically non-zero if you're talking about 3D. They could be zero, but not necessarily. Whereas in 2D, you know, you only have two non-zero force components and one non-zero couple component for a fixed joint. Okay, so let's see where we're at now. So here's our infinitesimal cube. And we have a force vector like this. And then we have a couple vector like this. And we have the same thing over here. And there's no reason that these have to have any relationship to each other.
What's a couple vector? And what's the notation you're using?
A couple, remember, a couple is a moment produced by a pair of equal and opposite forces. And the notation I'm using for a couple component is, I guess, in honor of the fact that it's two different forces, it's that doubled arrow like that.
So it's not a rotational force?
It's not a force, it's a moment, or it's a pair of forces that produce a pure moment. You have that in your statics notes if you want to go back and refresh your memory on it.
I'm kind of confused because we always used circles with an arrow.
We did that, that's true. We did that in 2D, and we did a lot of 2D problems. But in 3D, you can't really do it that way unless you're a very good artist, so it's easier to do it like this.
In which way is it rotating?
Okay, so the way it's rotating is according to the right-hand rule. So a positive value of this couple would be a rotation about this axis like that. Okay, this one would be a rotation like this. Remember, as all that stuff from before break coming back to a little. So each one of those doubled arrows is representing a moment component that's the direction is defined by the right-hand rule. Okay, now let's think about, so in our first thought about this, we have 6 faces, Each face has 3 forces and 3 couples on it. And so we have 6 faces times 6 loads gives us a value of a total of 36 loads to define this cube. Okay, that's a lot. And now, one by one, we're going to start thinking about things that limit the number of loads that we need in order to understand what's going on with this infinitesimal cube. What's the number of loads that we're going to eventually end up at? Just trying to... Yeah, right. So what we saw here is that in the end, we're only going to need 6 of these loads. And I'm going to just sort of explain how we're going to reduce from our starting number of 36 down to our final number of 6. Okay. So now, how does this reduce down to 6? Okay, well, first of all, if you think of a limiting procedure, like start with just a small cube and then limit down to a cube of size 0. All those forces are going to go to 0. And so forces, it turns out, isn't a really good way to measure the loading of an infinitesimal point. So this isn't going to reduce the number of anything, but as the size limits to 0, the force components would go to 0. So that's not helpful. We would just end up with this, this stress tensor where all the values are 0. It doesn't tell us anything. So we're going to replace the forces with force per area on the face. So now, as you limit this cube down to 0 length, the forces go to 0, but the cross-sectional, the face areas also go down to 0, and we end up in that limiting procedure getting something that's finite. So, okay, that's more useful. We're going to get some finite numbers out of this. And now our first reduction is, okay, let's replace the moments, those couples, with something like force per area times the distance between the forces. Okay, well, now we have something like, notice, if this is going to be a finite thing, the force per area is going to be a finite thing, but we're going to multiply it by a distance between these forces. That's what a couple is. That's going to go to 0. These all go to 0. And so we're just going to forget about worrying about any of the couples on any of the faces. Okay, so now let's see where we're at. So now we still have this cube. We have these things now that I'm going to give names to. I'm going to call this sigma xx, sigma xy, sigma xz, where the notation I'm using here, the first subscript is the face you're on. So this is the x face. And the second subscript is the direction that that component is going. So now on the y face, we have sigma yx, sigma yy, sigma yz. And then on the z face, we have sigma zx, sigma zy, and then sigma zz. That only shows 3 of these faces. There's 3 that are obscured. But now we've gone from 6 loads on each of these 6 faces to only 3. Okay, so now we have 6 faces times 3 loads is equal to 18 total loads on the cube. Okay. Well, we know we're going to keep reducing this down. Eventually, we're going to get to only 6 loads on this cube. So now let's think about the requirement that this is in static equilibrium, okay? And we're going to start with a force equilibrium. We're going to say that the forces add up to 0. The only way that you can have force equilibrium on this cube is for the components on opposite sides of this cube to have equal and opposite values. Okay, it's only possible if the components on opposite faces are equal and opposite. Okay, so now that doesn't reduce the number of loads on this cube, but it does reduce the number that are independent. If we know all the loads on, say, the positive faces, then we automatically know all the loads on the negative faces. Yes?
Would the face opposite XX being
Yeah, that we call that the negative x face, yeah.
so the force opposite to sigma XX would be sigma negative x negative x?
Yeah, well, so we're just, so if sigma xx has a value of positive 5 going in this direction, then back here on this obscured face, there's a value of 5 going in the opposite direction. And that's true of the other components too. So if this one is positive this way, then it would be positive going that way on the negative face. So all the negative faces are just mirror images of the positive faces.
So we won't ever need to name or label them.
Yeah, that's right. So we don't even need names for them. Exactly.
Okay.
Exactly. So how many loads have we cut out of our required listing?
We're down to 9.
We're down to 9, right? We cut out half of them. So now we have only 3 times 3 total loads required to know the full loading on this cube. Okay. And then the last thing we're going to do is require moment equilibrium. And the only way to have moment equilibrium, we'll think of it in 2D for a second now. But if this is our moment x, y, and this is our moment y, x,
Is it YX or YZ?
x. It's hard to think and talk at the same time. So sigma x, y has to equal sigma yx. And the same is true with xz and zx. And the same is true with yz and zy. Okay, so now how many more have we cut out? So, yep, and so in the end, 6 values of force per area specify the entire loading on that infinitesimal cube.
Assuming it's an equilibrium.
That is true. Let me write this. Specify the entire loading on the infinitesimal cube. And so we are in this class, and really in mechanics in general, we do assume that the things are in equilibrium. But remember that we're talking about engineering materials in engineering applications where we're talking about loads where we're worried about this material being damaged. So always when you picture a material, picture steel, okay? Like, and think about steel in a application where you're worried about it deforming so much that it develops permanent deformation. And then think about how much you would have to spin a block of steel in order to get loads that are equivalent to the kind of loads that we're talking about. You know what I mean? And so for engineering materials in engineering applications where they're in danger of being broken in some way, there just aren't cases. I mean, you could maybe come up with some cases, but for the most part, those inertia forces of something that's accelerating are just not going to be anywhere near the ballpark of the forces caused by contacts and things. Okay, so yes, we are always going to make the assumption that these things are in equilibrium, even when they're not in equilibrium, but that's going to give us really, really good approximations. Okay, it would be a little different if you were talking about a Jello cube, a Knox block. You can easily imagine spinning a Knox block enough that those inertial forces could cause permanent deformation, but it's a lot harder to imagine doing that for a block of steel. Okay, so we're down to our final uh, thing. And I drew this up above at the start. And we have, this is our, so let's think about the naming convention. This face over here on the right is our positive X face. You can think of, they're named after the axis that would poke out of them, you know, if it was like in Alien, you know, like, so this is the X face, and this is the one in the positive X direction. So this is going to be our sigma XX. This one is on the X face, and it's in the positive Y direction. So this is going to be our sigma XY. This is on the X face, and it's in the positive Z direction. So this is going to be our XZ. Now on the Y face, this is on the Y face in the Y direction. So that's our sigma YY. That was pretty crooked. This is on our Y face in the X direction, but moment equilibrium requires that this is the same as our XY. So I'm just going to draw that in there like that. Those are the same value. This is on our Y face in our positive Z direction. And now on the Z face, we have our sigma ZZ. And then this one has to, this would be our ZX, but from equilibrium, we know this is XZ. And this one would be ZY, but from equilibrium, we know this has to be YZ. And we will write this in the matrix, the stress tensor, in this way. So we'll have our sigma XX, our sigma XY, our sigma XZ. Then this next one would be our sigma YX, but equilibrium requires that this is equal to XY. YY, YZ. Now this one would be our ZX, but equilibrium requires that this is XZ. This would be our ZY, but equilibrium requires that this is YZ, and then ZZ. These values on the main diagonal are called the normal stresses. Look at that cube and tell me why you think those would be called normal stresses. Exactly. So those are the components that are perpendicular to the faces that they're acting on. Okay, so these are the normal stresses. And then the other ones are called shear stresses. And those are the ones that are parallel to the faces that they're acting on. Since normal stresses and shear stresses are sort of fundamentally different, like they're doing physically different things. Since normal stresses and shear stresses are fundamentally different, most people denote the shear stresses with the Greek letter tau instead of sigma, just to indicate that it's something else. So most people indicate shear stresses as the Greek letter tau. And so that stress tensor that I'll write like this, sigma with a undersquiggle saying it's a matrix, will in this class represented as sigma xx, tau xy, tau xz, tau xy, sigma yy, tau yz, tau xz, tau yz, and sigma zz. So this is the stress tensor. We're also going to often want to represent this in a form called the Voigt form. And so to represent this stress tensor in its Voigt form, you would give it as sigma xx. So we'd first do the three normal stresses. And then we'll do the shear stresses in, if you think about the order you would expect for the shear stresses, we're going to do it in the exact opposite. Seems stupid. I don't know why that's how people did it. I didn't get to decide. But you would think xy, xz, yz, it's in the exact opposite order. So it's tau yz, tau xz, tau xy. So these are the normal stresses. And these are the shears in backwards order. Okay, let's talk about the units of the stress tensor. I said that these values are force per area. So that means that if we're using SI units, which is what I'm going to do almost all the time in this class, this is units of newtons per meter squared, which is pascals. So two things to notice. For engineering materials, loaded enough that you care about the stresses. You know, if the material isn't anywhere near breaking, permanently deforming, anything like that, then you don't really care about doing stress calculations, you know. So if you're doing these stress calculations, for engineering materials loaded enough to care about the stresses the values are going to be, let's say, at least 10 to the fifth pascals. So expect big values on these stresses. And then second, stresses are often given in megapascals, which is 10 to the 6th pascals. And so make sure that your units match. You can do calculations in megapascals, you can do calculations in pascals, but you have to make sure that the units on everything match. Okay. Okay, let me do just one sort of example talking about stress tensors, Voigt stress, stress cubes, and then we'll get out of here. I know this today was a lot of just sitting and listening and writing and stuff. That's not how it's always going to be, but it's kind of unavoidable for this stuff. Okay, so here's the example. So let's say that we have a stress tensor that's equal to 5, 0, -1, 0, 50, 2, -1, 2, -10. And let's say these are all in megapascals.
So just a quick clarification, these stress tensor matrices are always going to be symmetric.
These are always symmetric matrices, that's right. Okay, so let's look at this and make sure that, so the requirement for this to be an acceptable stress tensor is that symmetry that you just talked about. So let's look at this and make sure xy is equal to yx, so that's good. Xz is equal to zx, that's good. Yz is equal to zy, so this is symmetric. And now what we want to do is first draw the associated stress cube. And second, give the Voigt stress. Okay, so here's our stress cube. The X normal stress is 5. The stress on the X face in the Y direction is 0, so I'll just leave that off. The stress on the X face in the Z direction is -1, so I'm going to draw that in the negative Z direction and just give it the value 1. And now I'll go to the Y face. So the normal is 50. On the Y face in the X direction, there's nothing, so I'll leave that off. On the Y face in the Z direction is 2, so I'll write that like this. And now on the Z face, in the Z direction, we have -10, so I'm going to draw that in the negative Z direction and call it 10. On the Z face in the X direction, well, it has to have this symmetry. but you can see that that's on the z face in the negative x direction, so this way. And then on the z face in the positive y direction, so this way. So those shear forces, those shear stresses, I mean, they always have to be pointing towards each other or away from each other, the matching ones. They can't be chasing each other. Okay. And that's how that symmetry shows up. Anybody have any questions about that? And then second, for the Voigt stress, we're going to start out with the normal stresses. So 5, 50, negative 10. And then we're going to go YZ, XY, XZ, and then XY. All these are in megapascals too. I just didn't write it everywhere, so it didn't get too cluttered. Anybody have any questions about those? Yep.
How many pascals in a megapascal?
10 to the 6th. So mega always means 10 to the 6th.
On my list of things to
We
write.
never really have to convert if they're all given the same.
Okay, right. So for now, you don't have to do any conversions or anything, but later when we start multiplying things together and stuff, it's when we introduce the compliance matrix and the stiffness matrix that we'll have to make sure that the units of the stiffness and compliance matrix match the units of the stress. Okay, but for now, yeah, we don't really have to worry about anything. Yep.
So for the quiz, if you want, I want to be ready for the quiz.
Yeah.
So what question we might get?
Okay, so yeah, I would be very likely to ask any of this stuff that says notice. You know, what does it take for two matrices to be multiplied together? What's the size of a matrix that you get for multiplying this times this? You know, all that kind of stuff. Does order matter? Does grouping matter? All this stuff. You're never going to be really responsible for anything having to do with this kind of derivation of what the stress tensor is. But it's probably pretty likely that I would give you a stress tensor or a stress cube and have you write the other one. You know, at the beginning here, I'm going to be trying to get you familiar with, like, get you used to connecting the different representations of this stress idea. I want you to get to the point where you look at those numbers and you just automatically think of what it looks like as a stress cube. Yes.
So I'm looking at this stress cube, and it seems to me that all of the forces are in the opposite direction that we would normally apply forces. Because if I have like a steel column, I'm gonna be looking at things pushing in on it.
Oh. Well, yeah, I mean, things also can be pulled on. You know, remember from structures and stuff, we'd have cases where things are in tension. So, yeah, anything that's in tension. So, yeah, so like this 50 here indicates that along that axis it's in tension. The 10 here indicates that along that axis it's in compression.
Thank you.
Yeah. Any other questions right now? Okay, so your homework, we don't have class, we don't have school on Monday. Your assignment is going to be due next Wednesday, a week from today, and it's going to be the rest of the vector stuff and just a small number of stress tensor questions. Okay, goodbye.
Will there be a quiz?
No.